In the late 1940s, American designers from Fairchild decided once and for all to rewrite the rules of military logistics. Why spend hours unloading crates on a frontline airfield under enemy fire if you can detach the entire cargo compartment right on the runway in seconds, secure a new one, and fly away immediately? The idea of detachable modular containers, which rules global trade today, first took to the skies on the experimental Fairchild XC-120 Pack Plane. But why did the US military, who showed great interest in the project on paper, close it immediately after the first real trials? How did engineers manage to get the aircraft to change its ground clearance for loading? And what hidden technical flaws caused this ambitious project to remain a single prototype? Today, we will analyze in detail the history of the plane with a box that was too far ahead of its time. The airfield hums with the roar of engines. A heavy transport plane has just finished its run along the strip and stopped in a far corner among intersecting taxiways. Ropes stretch from its hatches, chains clank, the wheels of carts creak. A dozen people in overalls bustle around the fuselage. One carries a crate on his shoulders. A second pushes a cart with equipment. A third shouts commands that are drowned out by the roar of the engines, which have not been shut down. An hour passes, then a second. The plane is still standing on the ground. This is not an isolated incident or a rare mix-up. This is a common picture for any airfield served by heavy military transport planes of the mid-20th century. Loading and unloading take hours, sometimes more time than the flight itself. Engineers tried to solve this problem for years. They accelerated the work of crews. They redistributed tasks. They combined technical maintenance with loading right at the parking spot, while mechanics checked the engines. Loaders carried crates into the adjacent compartment. And here's what is interesting. This barely helped. Even with the most coordinated work, the time savings turned out to be insignificant. It was not about the people. It was about the very design of the aircraft. The cargo compartment is one door, one passageway, one queue of people and equipment that physically cannot work faster than a certain limit. This is somewhat like a supermarket situation where a cashier tries to scan items faster while someone nearby is simultaneously restocking shelves. The processes run in parallel. But the queue at the cash register does not get any shorter because of this. In peacetime, such a delay would look like a frustrating flight delay, nothing more. But in a real conflict, minutes sometimes mattered. A plane idling on the ground for an extra hour is equipment that is not performing its task where it is needed right now. A question arose to which there was no simple answer. What if it is not about the organization of labor at all? What if the problem lies in the very idea of a cargo compartment built tightly into the fuselage of the aircraft? One aircraft factory in the United States of America in the late 1940s came to the conclusion that the answer required not an improvement of ground procedures. The answer required a complete rethink of how a transport plane should be designed in the first place. What the engineers of this company came up with looked almost absurd on paper, but in practice, it overturned the very principle of how cargo gets from the ground into the plane and back. On a drawing board in the design bureau of Fairchild lies a sketch that breaks conventional logic. Engineers had designed transport planes the same way for decades. There is a fuselage. Inside it is a cargo cabin. Cargo is placed inside, cargo is taken out from inside. No other options seem to exist. In the late 1940s, someone in this bureau asked a simple question. What if the cargo compartment should not be part of the fuselage at all? The idea sounded almost childlike. Take the cargo and move it outside the aircraft into a separate detachable block. The block is secured underneath, under the hull, as a suspended pod. You arrive, detach it, and fly away with a new one. Here it is worth stopping and understanding why this changed everything. Previously, planes were unloaded from the inside, slowly, through narrow doors, manually, or with equipment that barely fit in the passageway. Now, the entire cargo could be lowered to the ground in one movement, entirely. This is somewhat like how trucks with swap bodies work today. You drive up, unhook one container, hook up another, and drive on, without even looking inside. In the mid-20th century, such a thought was almost revolutionary for military aviation. The scenario went as follows. The plane lands at the airfield. The crew does not spend hours shifting cargo through a narrow door. the container is simply lowered to the ground entirely and another one is immediately raised in its place, already prepared in advance while the first plane was in the air. Refueling, a quick systems check, and the machine is back in the sky. All that multi-hour downtime we talked about at the beginning could simply not exist. But the idea opened up something more important than just speed. The same plane could now carry different types of containers. Today, conventional cargo. Tomorrow, entirely different contents. It was not the plane that changed, only its suspended part changed. The designers of Fairchild did not yet know whether this idea would generate interest outside their own bureau. But the drawings were ready. It remained to show them to those who make decisions about the future of military transport aviation. Representatives of Fairchild bring drawings and calculations to the Military Department of the United States of America. On the table is a scheme of an aircraft with a suspended container instead of the usual cargo compartment. The idea sounds unusual, but the military listens carefully. The late 1940s was not the calmest time for planning military logistics. The international situation required the development of the armed forces, and first and foremost, their ability to quickly transfer cargo and people where needed. A plane capable of reducing ground time literally to refueling fit into this task almost perfectly. The military department supported the project. The Army gave the green light for further development. The new machine was given an official designation. The plane was named XC-120, and unofficially, Pack Plane. The name caught on quickly because it accurately described the essence of the machine, a plane that literally carried a box under itself. And here's a small detail that is easy to pass by if you do not look closely. The letter X at the beginning of the designation is not a random decoration. In the American military equipment naming system, this letter is placed before the number of an experimental development not yet put into service. It was planned that after successful tests, the letter would disappear and the production version of the plane would receive a new name, C-128. Simply, the X would go, and a clean number of a serial machine standing in service would remain. The military seriously considered such a scenario. The customer showed interest not only in the concept itself, but also in the possibility of ordering containers of different purposes for specific tasks, from conventional cargo to much more specialized ones. However, the letter X before the number remained in place until the very end of this plane's history. Why, we will understand later when we reach the end. Meanwhile, having received the support of the military department, the designers of Fairchild set about the most difficult stage, turning a bold idea into a real flying airplane. And to understand what it was assembled from, we need to go back a bit, to the machine that was already in service. To build a plane quickly, it is not necessary to invent every detail from scratch. The designers of Fairchild understood this perfectly. They already had a ready-made transport plane in service, the Fairchild C-119, known by the name Flying Boxcar. Using ready-made assemblies instead of developing everything from scratch is a pragmatic decision. This accelerates design, simplifies future mass production, and reduces risks. This is much like how car manufacturers today build different models of cars on the same platform, changing only the body and part of the stuffing. The new aircraft was to take from its predecessor a significant part of the airframe, the power plant, and, what is particularly important, the two-boom design itself, a construction in which the tail unit is held not on one long tail, but on two separate booms on the sides of the machine. It sounds simple. In practice, not at all. The thing is that the basic machine was built around a conventional cargo compartment inside the fuselage. The new project, however, abandoned this compartment completely, replacing it with a suspended container. And that meant the fuselage could not simply be copied. It had to be designed anew, almost from scratch, only using familiar engineering solutions as a base. The same applied to the container. Formally, it relied on the fuselage design of the old machine, but in fact, it was a completely different detail designed for a new task, external mounting rather than internal. Take, for example, the nose part. If you look at the drawings from afar, it seems that the nose of the new container is just the nose of the old plane, slightly modified. But one has to look closer, and it becomes clear. The resemblance is almost accidental. The shape, proportions, mountings, everything was recalculated for new tasks. From the original, perhaps only the general idea of what the streamlined nose of an aircraft should look like remained. The engineers of Fairchild took a proven basis and built something completely new on it. and to understand how new, it is worth taking a look at what resulted in the end, starting with the fuselage itself. If you were to see the new plane without a container, live, from afar, you would hardly recognize a military transport in it. The fuselage received a shape similar to a drop, rounded at the top, with a flat bottom surface and sides smoothly transitioning into the roof. This shape was not a random whim of the designers. A flat bottom was required so that the container could fit tightly and securely to the fuselage from below without unnecessary gaps and distortions. In the very front part of the fuselage, they placed the crew cockpit. 5 people worked here, a crew calculated for the full control of a complex machine. All the remaining space of the fuselage behind the cockpit was given over to equipment, without a single cargo compartment inside, because the entire cargo was now outside in a suspended container. In the rear part of the cockpit and in the tail zone of the fuselage, they installed electric hoists. They were responsible for lifting and securely holding the container under the fuselage. Nearby, they placed locks that fixed the cargo in the desired position so that it would not shift by a centimeter during flight. And now, a detail that at first glance seems like a trifle, but in fact speaks of the level of thoughtfulness of the entire design. How did the crew even get into the cockpit of such a plane? The answer depended on whether the container was installed or not. If there was no container under the fuselage, a simple path went into action. In the flat lower part of the fuselage, there was a hatch with a ladder, and crew members climbed through it, like through a regular entrance to a plane. But as soon as the container was attached from below, this entrance turned out to be simply blocked. In such a case, the crew climbed into the cockpit in a completely different way, through the side doors of the container itself and a special hatch in its roof. It turns out that the same plane offered 2 completely different routes of getting to the workplace, depending on which configuration it was in at that moment. A trifle, but it was from such trifles that the whole logic of this unusual machine was built. The fuselage and cockpit were ready, but what held this construction in the air? The answer is in the wing, designed no less complex than everything else. The wing of this aircraft solved 2 problems at once. The first, familiar, to lift the machine into the air and keep it there. The second, much more unusual, to leave enough space under the fuselage so that a whole suspended container could fit there. The central part of the wing, the one that was attached directly to the fuselage, received a negative dihedral angle. Simply put, this part of the wing was slightly tilted down from root to tip, and not up as in most conventional aircraft. Why do this? Let's imagine for a second the opposite situation, if the wing rose up from the fuselage. The space under the plane would be reduced, and the suspended container simply would not have enough height for safe placement and lifting. The negative angle solved this problem directly. It lowered the root parts of the wing, freeing up space below exactly where it was needed, under the fuselage where the container was to hang. From these same inclined root parts, the wing transitioned into 2 long booms located on the sides of the center of the machine. It was on these booms that the tail unit was held, instead of the usual 1 long tail fuselage as in most transport aircraft at that time. On the outer side of each boom, the wing consoles were attached, continuing its span to the sides. The wing mechanization remained quite complex for a machine of this class. Flaps for controlling lift during takeoff and landing, ailerons for controlling roll in flight. On the leading edge of the wing, several air intakes were placed. Through them entered the air necessary for the operation of the power plant systems, the very one that was located a bit further in the front part of each of the 2 tail booms. This entire construction looked unusual even for an experienced aviation engineer of that time, but it was this unusualness that made possible the main idea of the entire project, a container suspended freely under the fuselage, not touching any load-bearing surface of the machine. The wing was ready to carry the plane. It remained to understand what exactly was to give this construction the speed and power necessary for flight with such a heavy load on the suspension. In the front part of each of the 2 tail booms, they placed 1 piston engine. The model was called Pratt & Whitney R4360 Wasp Major, at that time one of the most powerful production aircraft piston engines that existed at all. Inside, each engine worked 28 cylinders located in 4 rows in a circle. This layout is called radial. The cylinders diverge from the central shaft like flower petals if you look at the engine from the front. At takeoff, each of these motors developed a capacity of 3,250 horsepower. To feel the scale of this figure, let's imagine it differently. This is a power comparable to several dozen modern passenger cars working simultaneously, reduced to a single piston engine the size of a small room. And there were 2 such engines on the plane. Cooling 28 cylinders is not an easy task. Air for cooling entered through the front circular opening of the engine, literally washing the hot cylinders with a flow of incoming air during flight. These motors turned 4-blade propellers, large, heavy, capable of converting all this colossal power into thrust sufficient to lift a multi-ton machine into the air, together with the container full of cargo suspended under it. Standing next to such a plane on the ground at the moment of starting the engines, it was impossible not to feel this physically, a low, visceral roar that filled the entire space of the airfield, echoing with vibration even in the concrete underfoot. Power was resolved. But 2 such huge engines placed in the tail booms created a completely new headache for the engineers. Where to put the landing gear if a whole container was to hang from the bottom of the fuselage now? In a conventional transport plane, the landing gear solves one simple task: to hold the machine above the ground at a safe height and cushion the impact on landing. In the new plane with a suspended container, the task became many times more complex. The thing was that the basic model, from which the designers pushed off, already had compartments for retracting the landing gear right in the tail booms. But these compartments were designed for a completely different machine, the one that carried the cargo inside the fuselage and not under it. Now, however, a whole container had to fit under the fuselage, and that meant the landing gear struts had to not just hold the plane above the ground, they had to hold it high enough so that the container physically fit in this space, without touching the ground and without interfering with the operation of the lifting mechanisms. The engineers increased the sizes of the niches in the booms to accommodate the new, larger struts. The main supports with dual wheels of increased size remained in their places as in the basic model, but to them they added something new, a pair of front struts on each boom. These front struts received an unusual design. They were specially designed so that dual wheels of small diameter were led forward, almost level with the propeller rotation plane, a detail that in itself speaks of the density of this machine's layout. And now a question that is worth asking directly. Why would a plane change its height above the ground at all? The answer is simple if we recall the whole concept of the project. The mechanisms for adjusting the struts allowed changing the ground clearance of the plane, that is, the distance between the fuselage and the ground. This was done specially to simplify the process of bringing the container under the fuselage and its subsequent fixation. The plane literally squatted closer to the ground when the container had to be brought in or disconnected, and then rose to the desired working height. A small detail on the diagram turned into one of the key elements of the whole idea of quick cargo change. During flight, both struts on each boom retracted backward, freeing up space in the niches. The landing gear was ready. It remained to deal with the most important part of the entire construction, the container itself. All of what we have talked about up to this moment, the shape of the fuselage, the tilt of the wing, the placement of the engines, the landing gear device, was subordinated to one single detail, the removable container that hung under the plane and was the true heart of the whole concept. The container was a long construction of rectangular section, with fairings on the nose and in the tail part, giving it a more aerodynamic shape. Without these fairings, the container would look like a simple rectangular box. With them, however, it resembled more a full-fledged part of the plane. The nose fairing had an ogival shape, elongated, smoothly tapering to the front edge, similar to the nose part of an artillery shell, only much flatter. This fairing consisted of 2 parts that could slide apart during loading, opening access to the internal space of the container. In the left part of the nose fairing, there was a narrow door, a separate entrance not connected with the main cargo opening. The tail fairing was arranged in a similar way, but with a different shape. Its upper part remained straight, and the lower, the bottom, was tilted at a slight angle down. And here too, in the left fragment of the fairing, its own door was provided. The frame of this entire construction was assembled from a set of rectangular frames, transverse power elements, and many longitudinal stringers that ran along the entire length of the container. On this frame, metal cladding was attached, forming the outer surface. Worthy of special attention are the flat roof and the curved bottom of the container. It was here that the reinforced zones of the construction were located, zones that had to withstand the weight of the container when transported by plane, as well as when moving on the ground already without a plane, on its own wheels. And here it is worth stopping at one thought, to which we will return in more detail. The container was built not as a single, highly specialized block under one type of cargo. Its architecture originally allowed creating the most diverse contents inside one and the same external shell. From conventional boxes with supplies to things that were hard to imagine looking at the first drawings of Fairchild. But before moving on to what could be placed inside, we need to understand something else: how this container was raised to the plane and lowered back to the ground. To lift a multi-ton container and accurately secure it under the fuselage of the plane is a task that sounds simple in words, but in practice requires a system of mountings thought out to the smallest detail. On the roof of the container, several spherical support elements were located. The shape of a ball was chosen not by chance. It allowed the container to turn slightly and adjust to the position of the fuselage at the moment of docking, compensating for small inaccuracies during lifting. These spherical supports engaged with locks installed on the bottom of the plane, and after that, they were locked. From this moment, the container became, in essence, one with the fuselage, rigidly fixed for the entire flight period. The lifting process itself was performed by several electric hoists with remote control. The operator pressed a button, and the hoist cables began to slowly pull the container from bottom to top to the fuselage until the spherical supports entered exactly into their sockets. On the sides of the container, special devices were provided precisely for securing these cables, devices calculated to withstand the load from lifting a heavy, loaded block. And along the entire perimeter of the container's roof, in the place of joint with the fuselage, went a rubber gasket. It protected the connection from moisture, dust, and small debris, an unnoticeable detail but important for the long service of the mechanism. Now let's imagine the reverse process, unloading. The plane lands at the airfield, the locks open, the hoists slowly release the cables, and the container begins to descend to the ground. But it does not descend straight to the soil. In the front and rear part of the container, in the same place where the connection nodes were located, dual-wheel carts with self-orienting mechanisms were installed, similar to the wheels of an office chair, only calculated for a much greater load. As soon as the container stood on these wheels, it could literally be hauled away by a conventional tractor, the same one used for moving any other airfield equipment. No special equipment, no complex procedure. Unhooked, driven away, freed space under the fuselage for the next container. The mechanics were ready. It remained to understand, and who, actually, managed all this inside the machine itself. Before moving on, it is worth stopping and simply looking at the dimensions of this machine. Because figures in themselves rarely impress, but behind them stands a completely real, tangible scale. The length of the plane with a loaded container was 25.25 meters. This is roughly like lining up 6 passenger cars one after another. And that was just the length of the machine, without taking into account the height or wingspan. The wingspan reached 32.46 meters, more than the length of the fuselage itself with the container. And the height of the machine was 7.65 meters, which is roughly equal to the height of a 2-story house. The area of the wing was 134.3 square meters. For comparison, this is comparable to the area of half a standard football field, stretched into the shape of 2 narrow planes on the sides of the fuselage. The mass of the empty plane, together with the empty container, reached 18.14 tons. And the maximum takeoff mass up to 33.75 tons. The difference between these two figures is the weight of the useful load, fuel and crew, that the machine was capable of lifting into the air. And here appears a detail to which it is worth paying special attention. The division of the fuselage into a main section and a separate removable container did not pass without a trace for the carrying capacity of the machine. The new plane could carry 9 tons of cargo. For comparison, the serial basic model, the very one from which the designers pushed off, carried 12.5 tons, noticeably more. It turns out that for the convenience of a quick cargo change, they had to sacrifice part of the carrying capacity itself. How significant this loss was in practice, a question to which we will return a bit later. Meanwhile, for storing these 9 tons of cargo, inside the container there was a spacious compartment with a volume of 76.45 cubic meters. And here is what is interesting. This volume could be filled with a wide variety of things, not at all limited to conventional boxes with supplies. 76 cubic meters of free space inside one container is quite a lot. The question was not whether the cargo would fit, the question was what exactly could fill this space. The most obvious option, conventional supplies, equipment, machinery of suitable sizes and weight. It was under such a task that the project was originally created. The container arrives loaded, lands, detaches, and in its place they immediately lift the next. But the design allowed much more. Inside the same container, seats could be installed for 65 paratroopers, fully equipped, with parachutes and gear. One in the same external body, but completely different contents. The task changes, the contents change, not the plane itself. In exactly the same way, the container could turn into a place for transporting the wounded. Inside, stretchers were placed, and if necessary, a small medical point with the most necessary equipment for rendering assistance right during the flight. There was also another possibility, perhaps the most unusual of all. The container could be equipped for a mobile command post, a place from where they coordinated actions in a remote territory, where conventional stationary infrastructure simply did not have time to get. Let's imagine for a second the practical benefit of such an approach. The same airfield, the same plane, did not need to maintain a separate park of equipment under each of these tasks. Only a set of different containers was required, ready for use as needed. In the morning, a conventional cargo flight. In the afternoon, transfer of personnel. In the evening, if the situation required, evacuation of the wounded. And all this, one and the same aircraft frame, just with different blocks suspended under the fuselage. It was in this versatility that the main strength of the whole concept lay. The size and capacity of the container, as well as the ability to quickly change or drop it, opened up a much wider range of capabilities to the military department than any conventional transport aircraft of that time offered. On paper, everything looked almost flawless. But one thing is calculations and drawings, and completely another, how the machine would behave, breaking away from the ground for real. The calculated flight data of the new machine looked quite decent for a heavy transport plane of its time. The maximum speed reached 476 kilometers per hour. The cruising speed, the one at which the plane spent most of the flight, was about 340 kilometers per hour. The practical ceiling of height was limited to 6,700 meters, and the flight range was 3,700 kilometers. However, here it is worth making a reservation. All these figures changed depending on whether the plane flew with a suspended container or without it. The container, for all its usefulness, was also a rather voluminous obstacle for the airflow. It increased the aerodynamic drag of the machine and therefore reduced the real speed and range compared to the calculated indicators without cargo. Disconnected from the container, the same plane flew noticeably faster and further. Development of the project was completed in early 1950. Design work on paper ended, work in metal began. For the basis of the prototype, they took an unfinished serial plane of the basic model, with the factory number 10,312. This machine lost most of its fuselage. It was literally disassembled to free up space for the new experimental construction. From the dismantled part of the fuselage, they assembled one of the experimental containers, a solution in its own way symbolic. The old machine literally became the material for the birth of a new concept. According to available data, in the process of construction, they assembled several such containers in the cargo configuration at once. The wide use of already finished units and assemblies of serial equipment allowed to noticeably accelerate the entire construction. What in other circumstances could take years, here took mere months. The prototype was completed in early summer of 1950. Next, trials began, the very moment for which the whole project was started, the moment when drawings and calculations would either be confirmed in the air or not. On August 11, 1950, the experimental Pack Plane broke away from the ground in its first flight. The first flight passed successfully, but one successful departure still does not prove anything. The real check of the machine was only beginning. Throughout 1950, the experimental plane passed a series of ground and flight tests. They checked literally everything: how the airframe behaves in the air, how the power plant works, and most importantly, how the machine copes with the very essence of its concept, the rise and drop of the container. In addition to purely technical checks, the plane was involved several times in demonstration events. It was important for the military not just to get dry figures and reports, but also to see the machine live, to evaluate how quickly and harmoniously the change of the container occurs in practice. In 1951, the prototype was transferred to Eglin Air Force Base, located in the state of Florida. It was here that specialists of the Air Force were to give the machine the most strict and objective assessment. The goal of this stage was extremely specific: to determine the real operational characteristics of the plane in conditions as close as possible to those in which it was to serve, and on the basis of these data, to make a final conclusion whether it is worth adopting such a technique. The result of the checks turned out to be ambiguous. On one hand, the flight data of the new machine turned out to be practically identical to the indicators of the basic serial model from which it originated. The capabilities for transporting cargo were also in many ways similar, although the new plane was inferior to its predecessor in maximum carrying capacity, as we spoke about earlier. As an absolute plus, the military called the very possibility of quick container drop. This indeed significantly accelerated the preparation of the plane for the next flight. It was precisely for the sake of this that the whole project was started from the very beginning. The Commission was also interested in the idea of specialized containers for different tasks. But there were also claims, and they sounded serious. From the point of view of pure technical characteristics, the new plane looked, in essence, almost a complete copy of its predecessor, only with less carrying capacity. A natural question arose: does the convenience of quick container change justify this loss in cargo tonnage? To this was added another. In the construction of the machine, there was a significant number of completely new nodes and mechanisms: hoists, locks, adjustable landing gear struts, which had not yet had time to prove their reliability in complex, long-term operating conditions. And finally, the Commission had one truly fundamental question, which in the end determined the further fate of the whole project. Is it worth it all establishing serial production of a machine so complex and so expensive to manufacture for the sake of a benefit that in practice could turn out to be not so significant? The military department was to give an answer to this question in the very near future. In 1952, the Pentagon announced its final decision on the project. The military transport aircraft with a suspended container possessed a number of real advantages: quick cargo change, flexibility of application, the ability to turn one and the same machine into a truck, troop transport, or mobile medical point. All this remained true. But along with the advantages went the characteristic disadvantages that we talked about in the previous section: less carrying capacity compared to the basic model, complex, insufficiently proven mechanics, and most importantly, the high cost and complexity of mass-producing such an unusual design. Having weighed all the pros and cons, the customer made the decision to refuse the purchase of this equipment. Plans for serial production were canceled. The very letter X before the number of the plane, which we talked about in the third section, was destined to remain in place forever. The production version with the designation C-128 never appeared. The Army decided to go another way, to continue the operation of the already proven flying boxcars without supplementing them with new, more complex equipment. After the official refusal of purchase, the only built experimental plane remained, in essence, needed by no one. The machine was not required by the customer, who abandoned it, nor was it needed by the manufacturer itself, whose resources were now directed to other tasks. After some downtime at the airfield, the experimental copy was sent for disassembly. According to some reports, the machine was subsequently rebuilt back according to the original design of the basic serial model and included in one of the batches supplied by Army order. The plane, which was supposed to change the approach to military transport aviation, in the end dissolved among the most ordinary serial machines. If you look at the whole project as a whole, it is difficult to call it a failure in an engineering sense. The set task, to create a transport plane of modular architecture, capable of quickly performing operations with cargo and carrying the most diverse variants of useful load, was solved, and solved in a truly inventive way. But one successful engineering solution was not enough. Transport planes of traditional construction, for all their simplicity, remained more convenient and more profitable from the point of view of mass operation for decades. In subsequent years, the aviation industry of different countries returned more than once to similar ideas, planes with removable cargo modules. But not one of these projects reached full serial operation. Perhaps the point is not that the idea was bad, but